Okay, I would like to clarify 2 points that I did not fully explain last time. The first point is that I said that in the phase space, in mu space, if you have a volume element dx dp here like this, and then under free motion, it would become another shape. However, this distance is still dx plus order dx squared. And that is still true even if you consider collisions. And some ask me what is meant by this order. I'd like to just briefly explain it because that's an important point, the different orders of magnitude. I might just illustrate this by asking, how do you define a derivative? I find f of fx. How do you define df dx? How do you define this? This is defined as you take f of x plus delta x divided by delta x, and you take the limit as delta x goes to 0. That's the definition. Now, if we want to do this, this is equal to the limit as delta x goes to 0, 1 over delta x times, now we expand this in a Taylor series. So you have f of x plus f of plus df dx times delta x plus 1/2 second derivative times delta x squared and so forth. Now, this is first order, this is second order. Why is this negligible for our purpose? Because you divide by delta x. When you divide by delta x, you would get same thing here, except you f of x you would get f of x. No, but it's a minus f of x there. So I have here has a minus f of x. So these two terms cancel. So when you divide delta x, the first term is delta f delta x. There's no, this is canceled out. And the second term is 1/2 d2f dt squared times delta x. And so when you take the limit, this term vanishes. That is why second order small can be vanished in this context. And an appreciation of this one is important because in physics you want to make approximations and you have to consider the order of magnitude of things. And this is the preliminary definition, the most basic definition of order, first order, second order, and so forth. So this is the first point. The second point is that I did not quite derive the fact that this h always has a derivative that is smaller or equal to 0. So let me finish the derivation. Boltzmann's h is by the integral f log f, integral for p. I'm using a shorthanded to save writing, right? So you understand that when I say the integral for p, it means integral d3p. And therefore, dh dx, dh dt is equal to integral for p. We have delta f delta t times log f plus the second time you take f, and this 1 over f times df dt. So these terms cancel. So this gives you an integral over p of df dt times 1 plus log f. Now let us let it be p1. So this is integration, so I can just call it p1. And I want to substitute this from the equation of motion that we have derived before. this is just equal to df dt1, the collision term, because we are considering a uniform system. And this, of course, is just equal to integral p1, p2, p1 prime, p2 prime of the delta function of the final minus initial momentum, the T matrix squared, times f1 prime, f2 prime, minus f1, f2. Then you substitute this in. Oh, no, there's no P1 because it's only over P2. But when I integrate over P1 here, it completes the integral. So dH dt is equal to integral over all the P's, P1, P2, P1 prime, P2 prime, all the momenta in the collision, times d4 Pf minus Pi, the T matrix squared, times F1 prime, F2 prime, minus F1, F2, times 1 plus log F1. And I sort of just stopped here last time, and I just jumped to the conclusion. I'd like to supply the details here now. So now this is, now you will note that F1, this 1 is only an integration variable. You can call it something else. So we are free to relabel 1 as 2 and 2 as 1. So we interchange the labels 1 and 2. And the integral is the same because they are integration variables. So I relabel 1 goes into 2 and 2 goes into 1. And this is the same, this is the same, this is the same, but this becomes 1 plus log F2. The rest is the same. And this whole thing is equal to original integral. Therefore, I just take half of the sum. So I take half of the sum, so it's equal to take half the sum. And I'll get, I'll not write it out, it's just the same thing here. Here I will get 1 plus log F1 plus log F2 divided by 2. This is also equal to the same integral. Then now I know that I can do something else. I can interchange 1, 2, and 1 prime, 2 prime. So now I relabel 1, 2, replaced by 1 prime, 2 prime, and vice versa. And again, take 1/2 the sum. Now, what do I get here? Let us first just write what you get under changing. When you get this is equal to this sum here is the same, but I change a sign. Because in that bracket, we initiate 1 prime, 2 prime, 1, 2, it changes sign. Therefore, here it becomes minus 1 minus log F1 prime plus log F2 prime over 2. Minus sign here because that term changes sign. And if I write this the same before, I must change the sign here. So now I can take 1/2 the sum. And I would get the same thing here. Here, these two cancel. I would just get log F1 plus log F2 minus log F1 prime minus log F2 prime divided by 4. And now, this is the result that I jumped to last time. Because now this term times this bracket is never positive. So now I have dH dt is equal to integral over all the momenta, P1, P2, P1 prime, P2 prime, this delta function, this T matrix squared times F1, F2, F2, 1 minus F1, F2 times log of F1, F2 minus log of F1 prime, F2 prime, 1/4, and this term is always less than or equal to 0. And therefore, I conclude that the time rate of change of S is never positive. And this is called the H theorem. We will later come back to this and discuss that this is the statement of the second law of thermodynamics, because H is the negative of the entropy. We will come to that. But the last time we use this in the sense that there also shows that dH dt is equal to 0 if and only if F1 prime, F2 prime minus F1, F2 is equal to 0. So this sets up this as a necessary condition for equilibrium. And with this, we have proven that that condition is both necessary and sufficient for equilibrium. And we saw that last time, and we get a Maxwell-Boltzmann distribution. And if you remember, the Maxwell-Boltzmann distribution now is independent of the time. It only depends on the momentum, because we are considering a spatially uniform system, so there's no spatial dependence. So the Maxwell-Boltzmann distribution function, which is F0 of P, is equal to some constant times e to the minus alpha P squared. And we determine these constants by the condition that the integral of F0 over all P must be the density, and P F0 integral of P squared over 2m is the energy density times n. That is this divided by integral F0 over P is equal to energy per unit volume. So we can express the two constants, C and alpha, in terms of the observed quantity's density and the energy per unit volume. And last time we showed that we did some Gaussian integral, you remember. And we find that epsilon is equal to 3 over 4m alpha. And alpha is just equal to 1 over 2m kt. This case is Boltzmann's constant. So now we have this distribution in terms of the average energy of the system. However, we don't really directly observe the average energy of the system. What we measure is things like the pressure. So let's compute the pressure of the system and express epsilon in something that is directly measurable. So we're going to calculate the pressure of the system. What is pressure? Pressure is there's a wall. Pressure is a force per unit area. Exerted by the gas on the wall. Let's take a unit area here. The gas comes here and bounces back. It comes and reflects back. And when it bounces back, it imparts momentum to the wall. And the time rate of change of that momentum is the force. So all we have to do is to calculate the momentum that is imparted by the gas to this wall per second, per unit area. Now this is easily computed because we have the distribution function. We know the distribution function, so let us compute it using this definition. Let us call this the x-axis. Then all that matters is the x component of, suppose this is velocity, it's proportional to the momentum, right? All that matters is the x component of this Vx, this projection. Because upon a collision, Vx is reflected. Vx comes in and Vx goes out. So that in one collision, the momentum is 2mVx imparted to the wall. It comes in, it goes out. And it doesn't matter whether this gas has a y component. The gas could come in like this. As long as it's the same Vx component, the momentum imparted to the wall is the same. It's the x direction that's normal to the wall that's important. So now let us consider the following construction. Suppose this is wall. I take a unit area here. Suppose I construct a cylinder, normal to the thing, whose length is Vx. And this is unit area. You will agree that all atoms in the cylinder indicated there will hit the wall. All atoms with velocity component Vx will hit the wall. Per second, in 1 second. The velocity is Vx, so I take a tube with a length equal to that. So in one second, all the atoms will be hitting the wall. Now each hit loses momentum 2px, which is 2mvx to the wall in part times momentum. And the number of atoms reflected per second is equal to Vx times F0p times d3p, if Vx is greater than 0. You see, this is the flux of particles, right? This is the number of particles. This is the density, right? This is the density of particles with Vx. So the density times Vx, and that's just equal to the density here times this volume of the cylinder, unit area. So that's the number of atoms hitting the wall per second. And when it hits, it reflects. And therefore, we can now write down the pressure is therefore equal to. You take the number of atoms, Vx, F0p, d3p. This is the number of atoms hitting the wall. And in each hit, the momentum is 2px. And then you have an integral over all p such that Vx is greater than 0. And this is the formulation. And now we know what F0p is, so we just plug it in and calculate this. So now Vx is equal to px divided by m. And F0p is c times e to the minus alpha p squared. And, all right, so this is equal to c times integral Vx, so that Px is greater than 0, d3p times this in 2 over m times E, there's a Px times Px squared, with the 2Px, times e to the minus alpha p squared. Alpha squared means Px squared plus Vy squared plus Vz squared. Since this integral is, the integrand is the same whether you take minus Px or plus Px, this is just equal to 2c over 2m over all of the space without this condition times Px squared times e to the minus alpha p squared. Now, since there's no difference between x, y, and z, you can replace x by py, pz, p or pz, and the result is the same. And therefore, you can replace px by 1/3 of p squared. P squared, namely p squared, is equal to px squared plus py squared plus pz squared. With that, you have a perfectly simple looking integral. This 2 goes to c over m integral d3p p squared e to the minus alpha p squared. And we have done this integral before because that's proportional to the energy. So without ado, you can write down the answer immediately. P is equal to 2/3 times the density times the energy per unit volume. And epsilon was given here in terms of alpha. Therefore, it is equal to 2/3 n, and epsilon is 3/2 kT. This is Boltzmann constant. And the 2/3 steps cancel. You just get n kBT. No, that's not right. No, I don't want that. Epsilon is equal to, I want to substitute from an earlier expression. Epsilon is equal to 2/3 m. Epsilon is equal to 3 over 4 m alpha. So this gives me alpha on this side. But I might as well just keep it this way. So now the energy density is given in terms of the pressure. And we measure the pressure. And we know experimentally the pressure for an ideal gas defines a temperature scale. The ideal gas temperature scale is defined by, it's called T, which coincides with absolute temperature. As you know, PV is equal to NKT. This is fine T. So if I compare both sides, I conclude that epsilon is equal to 3/2 kT. And that alpha is equal to 1/2 mkt. So now this is the ideal gas law. You notice that we have the T is a definition. It's just defined as PV. You take PV, you divide it into equal intervals, and you call it T. And the Boltzmann constant, Kb is a constant, in order to supply the unit, the degree Kelvin, and n is the number of particles. And therefore now F0, now we're going P is equal to C e to the minus p squared over 2m kT. Sometimes I leave out the Boltzmann B if it's not, if there is no confusion, because just to save writing. And C is equal to N over 2 pi m kt to the 3/2 power. And that is the Maxwell-Boltzmann distribution expressed in terms of temperature. Now, the T coincides with the absolute scale of temperature. The thing that is added to this by thermodynamics is that T cannot be less than 0. There's a lower bound, and that's called absolute 0. From the ideal gas, you can also tell that PV cannot be negative, so you know physically, so you know the T should be bounded from below. And that bound is called absolute 0. So now that's our first result in thermodynamics. We have derived the equation of state of an ideal gas. PV is some function of the temperature, and we'll call it the temperature. Now, you know that you could sometimes you go PV is equal to NKT. That's one way of doing it. Some people also write PV is equal to nRT, where N is the number of moles. This is the number of particles. Number of atoms is the number of moles. And therefore, NK is equal to nR. And R is called the gas constant. And therefore, N over small n is equal to K over R. And N over N is the number of particles in a mole. Therefore, this is Avogadro's number. So these three constants, K, R, and A, are related. Boltzmann's constant, the gas constant, and Avogadro's number are all related. And I don't have to give you the figures. You can look it up. Boltzmann's constant. You know, KT, K always goes with T because T is a temperature. K is put in to convert it into an energy, into quantity with the measured energy. So if you try to measure temperature in energy units, you can just set K equal to 1. That's usually done. So that is our first step into thermodynamics. So now let's discuss thermodynamics. Now let's derive the thermodynamics of an ideal gas. Since we know F, we know everything about the system. The first thing is that we should compute this Boltzmann's H in equilibrium. So H in equilibrium, we call it H0, which is equal to integral over P F0 log F0. You put in Maxwell-Boltzmann, you just compute it. What is this equal to? It is equal to, from there you get C integral over P e to the minus alpha p squared. Then you have log C e to the I minus alpha p squared. And this is equal to C integral over P e to the minus alpha p squared times log C minus alpha p squared. Usually every integral, you know how to do it. This is just the Gaussian integral. This is Gaussian integral times p squared. All these integrals you can do. But its quicker way is that since we have done those integrals before, you just note that, let me rewrite this. This is the first one is C log C times the integral over P of e to the minus alpha p squared. The second one is minus alpha times C integral over all P of e to the minus alpha p squared times p squared. This is just n, the density. And this is just equal to 2m times n times epsilon. 2m because I will put a 2m here, that's the energy. And so this is equal to Let me just give you the final answer. You can work out the algebra. You can put this together, and the final answer is equal to, I can write it as n over v, which is small n, because I like to keep n and v separate, so just this one, times the natural log of n over v divided by 2 pi mkt to the 3/2 power minus 3/2. So now we have this Boltzmann's h, which is the minimum value of the h in equilibrium. That is, when the system approaches equilibrium, h just approaches this. We will now show that this is proportional to the entropy of the system. To do this, we start from the first law of thermodynamics. As you know, there are two laws, the first law and the second law. The first law is a statement that heat is a form of energy. And the second law is a definition of the entropy. It says that the entropy, it states the connection between the entropy and the heat. So let us define the internal energy. Now this is thermodynamic. The internal energy of the system U is just equal to the number of particles times the number of particles per unit volume. And this is equal to, we know what epsilon, so this is 3/2 nkt. And this is a well-known result. For an ideal gas, the energy depends only on the temperature. And this immediately gives you that the heat capacity is 3/2 nk. And the entropy, we claim S is minus n k, this is k, Boltzmann's constant, times H0. Right? So that is equal to, it is equal to, if I use the result from there, it is equal to minus kn times log of n over v times t to the 3/2 power. And all this junk, 2 pi m and so forth, they're constants. I'm going to take them out. The 3/2 too. So this plus a constant. This assumes that n is a constant also. Therefore, up to a constant, S is signified by this, according to our computations. Now to show that this is the entropy, you take the differential of this, ds is equal to minus kn, that is, n is a constant. The only thing varies is v and t, times d, let me just log n minus log v minus 3/2 log t. And when you d, that constant goes out. And the differentials are kind of straightforward. You get minus kn times the log n is a constant, so that doesn't contribute. So it's minus dv over v minus 3/2 dt over t. And if I just multiply this inside, I get the minus signs cancel. I just get n kt divided by v times dv plus 3/2 n k dt. Now you will note that this is just du. And this is p by the equation of, so this term is just p dv. So according to this formula, ds s is the entropy of the thermodynamics, because now we have to reach a du is equal to minus p dv plus t ds. You will multiply both sides by t. This t doesn't belong here, does it? Let me see. nk over v d, yeah, this is equal to this. So I see. So t ds is equal to, I put a t here and I cancel the t here. And then I'll get a t here and I'll get whatever here. So now this says that TdS is the heat added to the system. And that's the second law of thermodynamics. Now here, everything applies only to the ideal gas. Later, when we talk about statistical mechanics, we'll do all this for any system. But here, I think you can appreciate that we started from some Newton's law, but we have derived thermodynamics in ideal gas. So now if S is the entropy in equilibrium, then we must have, then when not in equilibrium, we must have ds dt is greater or equal to 0 from the H theorem. And this tells me that the entropy of the universe never decreases. It always increases. And that's also a statement of the second law. Now, this is very troublesome. This is a profound statement, but very troublesome. So let us consider the meaning of this. And this is a very difficult point to get across. It's a thing that puzzles people all the time. I cannot write down all the arguments. You just have to listen to me, try to understand it, and later go home and write it down in your own words. In the 19th century, when it was thought that all these things are exact, that was before Boltzmann derived this, they thought that the second law is exact. And the entropy always increases. And therefore, the universe will reach a state of maximum entropy. That's called the heat death of the universe, that we all go marching towards an end called the heat death of the universe. And also, everything in the universe develops with a certain sense of time, the direction in which the entropy increases, and that's called time's arrow. We all feel it. It's time's arrow pointing to something, pointing to death. Right, from birth, and then your time's arrow points to death. Everything. And when Boltzmann derived this from mechanics, people thought that this cannot be right, because the fundamental equations of classical mechanics on which he derives his equations is invariant under time reversal. So how can you have something that has time's arrow from something that has time reversal invariance? This hounded Boltzmann all his life. I think he committed suicide, and people said partly because of that. Now, how do we understand this? I think we understand it, but it's not easy. Now, first you have to realize that this is not the exact statement, because we have made an approximation. We have neglected correlations. That is, we have approximated a two-particle correlation function with a product of two diffusion functions in the key step in Boltzmann's equation. That's an approximation. And that makes this result inexact. So that thermodynamics is not exact. It's only correct in the limit of large number of particles. How does a true S look like? It would look something like this. This is S as a function of time. According to our thing, it will just smoothly go up forever. But actually, it looks like this. These are the fluctuations that we have neglected because of correlation. In these small fluctuations, ds dt need not be greater than 0. It should be negative. It's when you neglect these small fluctuations that you can get the smooth rise. But even the smooth rise is not always. Sometimes you could suddenly jump and then go on again. And these are small fluctuations. And this is a large fluctuation. The small fluctuation is always present. It's Brownian motion. He says we don't see it. They're always present. And this is Brownian motion. The large fluctuations happens with such a small probability that we can say that it never happens. Very improbable. So we just ignore that. When we ignore that, we get a second law of thermodynamics. So you ask, how improbable is this? How improbable is it? What kind of fluctuation would this be? This would be something like, I put this eraser here. This is not flat, isn't it? I put this eraser here. See this eraser here, right? And all of a sudden, it flies up in the air, comes down. Is that possible? It's not a violation of mechanics. It might happen that all the molecules, I need to just push at this eraser at that time and just push it up. Mechanics allows it, but it's very improbable. In your everyday life, you can safely discount it. If you act as that this could never happen, that's the second law of thermodynamics. However, you might say, oh, that's very improbable, but you make this eraser smaller and smaller and smaller, there will come a point where it performs Brownian motion. Then it is not only probable, it's a certainty that it will do this fluctuation. The borderline is fuzzy. If you reduce this eraser to a nanometer, you will see Brownian motion. And there's no cutoff. It's just when it's large enough, you say, I can ignore the Brownian motion. I can ignore these large fluctuations. And when you do that, you get a second law of thermodynamics. So that's point number one, that the second law of thermodynamics is a result of ignoring the very large fluctuations. And that is very reasonable in everyday life. But it's incorrect for a nanosystem. For a nanosystem, you are in this region. It's always fluctuates. And in between, from a nano scale to this scale, there's no cutoff. The fluctuations gets more and more important and so forth. So you see, I cannot write all this down, right? So I hope that you can try to understand this and maybe go back and write it down in your own words. Now it comes to the point of times arrow. Times arrow could be formulated this way. Suppose I show you a movie. frames. I tell you, can you tell which frame comes first? Because the movie is following. Of a box. This box is divided into two partitions, and there's a hole. One frame is, there's a lot of gas here. Second frame is this. The third frame is this. 1, 2, and 3. There's a T1, T2, and T3. Now, every sensible person will say that T2 comes later and T3 comes later. So you must have this. And that's times arrow. You say that's common sense, right? If somebody shows you a movie like that, you will not hesitate to do that. But is the reverse motion a possible motion? Of course it is. You can prepare a gas so carefully here that it all goes in back here and goes to the other side. But you have to prepare the gas very, very carefully, right? All the positions, velocities have to be carefully tuned to a very precise accuracy. If it's just one molecule deviates the velocity by a little bit, it will not do this. It will not go back. The genie will not go back to the bottle. So this is times arrow. Times arrow comes from this. We conclude that times arrow comes because, one, there are a large number of particles. Two, the initial state is improbable. So it's a function of this. Why is this state improbable? Because if you consider the phase space of this thing, the fact that the gas occupies this one side is a very small area in the phase space. So it would like to go into a bigger area. And so the improbability of the initial state gives you times arrow. The state would like to go to an improbable situation to a more probable situation. And that's not an arrow in time. This is a probability. Consider the next example in which I don't have a large number of atoms. I draw the same picture with a field, with a smaller number of atoms. So you have 3 atoms. In the second frame, it looks like this. In the third frame, it looks like this. Perhaps. Maybe like this. Now, can you tell which comes first? You cannot. Because the initial state is very probable. It's one of the typical states. So is the final state. So there's no times arrow in that picture. Times arrow comes when you have a large number of particles and when you have an initial state is improbable, right? That don't cry over spilt milk, right? Because you cannot put the milk back. Why? Because it is very improbable for the milk to be found in the bottle. Somebody has to put it there. So as I say, it's not easy to understand these things. But I hope you understand this well enough. So go back and think about it and restate it in your own words. And now we go on. Let's take a break.